Acids and Bases, Part 2, a molecular level model of acids and bases. In this video, you will learn how to distinguish acids and bases by their submicroscopic properties. Some key terms in this video will be the Arrhenius definitions of acids and bases, the hydronium ion, and the hydroxide ion. The most important ion in the study of acids is the hydronium ion. The hydronium ion is simply a hydrogen ion covalently bonded to a water molecule, changing H2O into H3O+. This polyatomic ion, H3O+, hydronium, is not on the ion formula chart on the back of your periodic table, so you'll have to memorize this ion. Don't worry, the hydronium ion is essential to the study of acids, so you're going to see it a lot. By the way, because a hydrogen ion, H+, is basically just a proton, you can also think of the hydronium ion, H3O+, as a water molecule with an extra proton attached. The earliest definitions of acids and bases had to do with how they behaved macroscopically, but a modern definition of acids has to do with how it behaves submicroscopically, on the molecular level. According to what is called the Arrhenius definition, an acid is any substance that produces hydronium ions when dissolved in water. If you put it in water and hydronium ions are formed, then it's an acid. Here is the general reaction for a generic acid, HA, in water. The HA molecule will react with the H2O molecule to produce the H3O+ ion and the A- ion. This equation is balanced, so we will not need to add any written coefficients. Recall that H3O+ is the hydronium ion formula. The A- is the formula of whatever ion is left over when the H+ in the front of the acid formula is removed. Before we look at a couple of specific examples, let's visualize what's happening on a submicroscopic level when the acid HA is placed in water. This is the mental picture you want to have every time when you visualize what's happening when an acid reacts with water. The arrow shows that the H+, a proton, in the front of the acid formula is removed and attaches to the water molecule. This produces a water molecule with an extra hydrogen atom and a positive charge, the hydronium ion. The A- is the anion that's left over when one H+ is taken off of the front of the HA acid molecule. Now let's look at two specific examples and apply the generic equation to them. The first example is the acid that's found in your stomach, hydrochloric acid. It's also known as muriatic acid, and you can buy it at the hardware store for cleaning cement. Hydrochloric acid's formula is HCl, so the A and A- from the generic equation will be replaced with Cl and Cl- in this example. We see that HCl, hydrochloric acid, reacts with H2O, water, to produce H3O+, hydronium ion, and Cl-, the chloride ion. As shown in this equation, hydrochloric acid is an acid because it produces hydronium ions in water. The second example is the acid found in vinegar, acetic acid. Acetic acid's formula, HC2H3O2, is a bit more complex than the previous example, but we'll apply the generic equation from earlier in the same way. The A is C2H3O2, so A- is C2H3O2-, which is also known as the acetate ion. Therefore, we have HC2H3O2, acetic acid, reacting with H2O, water, to produce H3O+, hydronium ion, and C2H3O2-, acetate ion. Again, as demonstrated with this equation, acetic acid is an acid because it produces hydronium ions in water. Now let's change gears completely, and let's take a look at the submicroscopic world of bases. Hydroxide ion, OH-, is the most important ion for bases, and you're already familiar with it from your previous studies in chemistry. It's even on the back of your periodic table on that ion formula chart. Whereas hydronium was a water molecule with an extra proton, H+, the hydroxide ion is simply a water molecule with a proton, a hydrogen ion, and H+, removed. The Arrhenius definition for bases states that a base is any substance that produces hydroxide ions in water. If you put it in water and hydroxide ions are produced, then it's a base. Most bases are simply metal hydroxides, that is, ionic compounds with a metal cation and hydroxide for the anion. In this generic equation, we use B to represent the metal, so B plus is the metal cation. In this equation, we are considering only a metal with a 1 plus charge, but it could be 2 plus or 3 plus, and in those cases, there would be more OH minus ions, so coefficients would be needed in order to balance the equation correctly. Do you recognize this generic equation? Have you seen anything like it before? If you've ever written the equation for the dissociation of an ionic compound in water before, then you've seen this process before. To visualize what's actually happening on the submicroscopic scale, think of it this way. The cations and the hydroxide anions are being separated, dissociated, from one another as they dissolve in water. Because the anion is hydroxide, this makes this particular kind of ionic compound a base. Again, this reaction is nothing more than the dissociation of an ionic compound. Here are two examples of balanced equations demonstrating the Arrhenius definition of a base. Sodium hydroxide is a metal hydroxide, so Na and Na+ will be used instead of B and B+ from the generic equation. This also gives us NaOH, sodium hydroxide, dissociating into Na+, a sodium ion, and OH-, a hydroxide ion. This shows that sodium hydroxide is indeed a base because it produces hydroxide ions in water. For magnesium hydroxide, it is slightly more complex because magnesium is a group 2 metal and it forms a 2+ ion. This means that we'll have to balance the equation once we write it out. But Mg will take the place of B, and Mg2+ will take the place of B+ in our generic equation. This gives us Mg parentheses OH2, which is magnesium hydroxide, that dissociates into Mg2+, magnesium ion, and 2 OH-, hydroxide ions. And once again, we see that magnesium hydroxide is a base because it produces hydroxide ions in water. Besides metallic hydroxides, some molecules that do not contain hydroxide ions can produce hydroxide ions in water, and are also, therefore, by definition, bases. Ammonia, NH3, is the most important example of this kind of base. In this reaction, it is ammonia that is taking a hydrogen ion from the water molecule, turning the water molecule into the hydroxide ion. The process also produces NH4+ ion, which is the ammonium ion that you are probably already familiar with. The process is shown here, but to summarize, a proton, H+, leaves the water and bonds to the ammonia, producing ammonium ion and hydroxide ion. If you recall from your previous studies in chemistry, an electrolyte is a substance that will conduct electricity when dissolved in water. Pure water does not have any ions dissolved in it, so it will not conduct electricity. Pure water is a non-electrolyte. Once an acid is dissolved in water, according to the definition of acids, hydronium and other ions will be present. So an acid is an electrolyte and will cause the water to conduct electricity. Similarly, because bases will produce hydroxide and other ions when dissolved in solution, bases are also electrolytes and will conduct electricity in water. To recap, in this video, you learned how to distinguish acids and bases by their submicroscopic properties. Thanks for watching.